Levitating Balloons Lab, Hannah Boardman and Riley Eubanks.
Our team wanted to investigate how different magnitudes of charge can affect two charged particles. Our null hypothesis says that two balloons have a magnitude of charge. We can just give them that. But the magnitudes don't affect each other. Our alternative hypothesis puts forward that the two balloons may have a magnitude of charge that is affected by the transfer of electrons, and those magnitudes can affect the two balloons.
To understand why the balloons interact the way that they do, you have to think about the forces acting upon them. This can be shown through the use of a free body diagram that illustrates the forces on each balloon and where they are coming from. Each balloon has force gravity acting on it, an electric force from the other balloon, and a tension force from the string. The system schema depicts the same process with all the components and their relationships visibly accounted for. This includes the electric interaction between the balloons, the contact between the string and the balloon, the contact between the string and the meter stick, and the contact between the balloon and the sweater, which is out of the system. Here you see what our assembled model looked like. Each balloon was attached to the meter stick with a string. When given more swipes, the angles seemed to decrease, which can also be shown here. Each balloon was given the same number of swipes, so we expected their charge to be the same. Thus, the forces will move them an equal amount from the midline. However, even if the charges were different, R is affected by the product of the charges, so the pair of the charges would affect force and R equally. Because of this, the electrical force would be shared equally, thus leading to identical angle changes. First, we assembled the model as shown in the last slide. Then we began our experiment. We started out by not giving a charge to either balloon and just letting them interact without inputting energy. Then the angle between the string and the positive x-axis were recorded, as well as the distance between the balloons. Following this, we gave a different number of swipes to the balloons. In each trial, both balloons were given the same number of swipes. So in trial 1, which was used as a baseline, they each had 0 swipes. In trial 2, they each had 4 swipes. In trial 3, they each had 8 swipes. And in trial 4, they each had 16 swipes. The angle and R were recorded for each trial. We measured R when we noticed the least amount of movement between the balloons and rounded this to the nearest centimeter. Both balloon 1 and balloon 2 weighed 4.2 grams. This chart shows the data for the R and the angle between the string and the positive x-axis for each trial. From this information, we can see that as the number of swipes on the shirt increased, so did the R. In addition to this, as the number of swipes increased, the angle between the string and the positive x-axis decreased. Hence, the balloons moved further apart as swipes increased.
We began the trials with a 0 charge. We tied a balloon to a string from a meter stick and had them hang about 4 centimeters apart, just at rest. At the beginning of each trial, we held them down at cosine 270, that's straight in the y direction. And then we released them and recorded the degree of separation from the axis and the stick to the R distance between the two balloons. Trial 1, we found no movement, but as we increased the number of swipes, we saw the angle continue to change. Now to the fun part. So, I split up the forces acting on balloon 1 into the x and y components. That's fun, you can see what's going on, then you get your net equation, move some stuff around, suddenly sine over cosine, so you have tangent. Weird. I isolated the Q value because Coulomb's constant was in there, and now I have this formula, tension by tan theta r squared over K, and then that cosine 180, so we understand which direction we're facing. So now time to solve for Q. So accounting for all the forces, you find tension, then you can go through each trial's calculation and find the Q charge. So you noticed how the first trial, it was exactly tan 270, which is 1 over 0, which I think is really interesting because it means that it is a non-existent charge. It just couldn't happen. And because there was no charge there, it was just resting at the complete negative y-axis, no force in the x direction. After that pitfall, we only have trials 2 to 4 to work with values. So you see on trial 2, there's a nice 2.4 to the negative 6 charge. Nice. But as trial 3 and 4 comes, you see the number go down. Confusing at first. But then we really put to realize, wait, it is gaining more electrons as it continues to be swept against the shirt. Now that we've found the charges for each of the balloon's trials, we can find the electrons that made those charges. By just taking whatever the charge we found to be on the balloon and dividing it by the value of what an electron is charged, we can just see how many electrons went over there.
There were possible mechanical errors with measuring as well as with potential for charge transfer from our bodies. There were also trouble with neutralizing the balloons, which could have caused problems with the electrons. Overall, our initial hypothesis was correct, and as the swipes increased, so did the number of electrons transferred, which could have been due to electron affinity.